Ever seen Wayne's World? Long time ago. 5, 4, 3. Sorry. 89, right? Yeah, I know. I know. I was about 65 at the time, but I still was able to go see it. I had just gotten out of the hospital. I had a hip replacement. A couple things I wanted to note about the last section. So in our class, for the most part, actually through all of class, with the exception of the last week scheduled, our latent variables we're going to assume to follow a normal distribution, the continuous. Last question. So that's the general thought, is the latent variables are continuous. What we also put with that is the idea that we saw in the first week's lecture. We have these series of simultaneous equations. So when we have a latent variable that we're measuring, we don't add up the variables. We just say, oh, we have 5 regressions with this thing we didn't observe. Those regressions all assume a normal distribution for error. And so we're going to keep that in place through most of class also, just to get the structure of everything down. When we get to the end of class, we start talking about generalized models and so forth. We will change that up a little bit, and things will be a little bit different. So for instance, categorical data. If you have zeros and ones, for instance, for your data, and you want to measure a trait with it, we'd have to assume not what we're assuming in our first example. We'd have to go with a different type of distribution for it. That's actually where IRT comes from. The idea of IRT, what you learn in IRT, and again, labels are, we can kind of nuance the labels, but generally speaking, you have a factor or a latent variable, a trait, we call it ability, but still latent. It follows a continuous normal distribution, and it's measured by items or variables or data that are categorical. Zeros and ones, maybe 0, 1, 2, something along those lines. So everything that you learned about here, you'll learn about there again. So I like this, if we can sort of kind of break down the labels a little bit and just kind of get the approach, you get a multiplier of what you've been through in terms of class. In IRT, you get every field has its nuances, so SEM, they'll be theirs. IRT has its. I don't know, every field does. But case in point, a little bit differently, right before we had class, as part of my other part of my job, we had a technical advisory committee meeting, which means we had a bunch of professors from different states on the phone for this project I work on. I work on the Dynamic Learning Maps project. Some of you are familiar with it. For those of you who aren't, it's a project where we're trying to measure thousands of latent variables across all of elementary and high school. Right? I'll put it shortly. Those latent variables, the TAC phone call is kind of like another dissertation defense sometimes. You say, here's what we'd like to do, and then you have these professors weigh in on it and whatever. And I was telling Megan, kind of recapping it, I kind of like it because I like the sparring with it now. It kind of shows me how far I've gone in terms of, my dissertation defense went poorly, but now I feel like, I can swing back a little bit, and just not like physical altercation, mental swinging. But on that note, one of the things that we noted today that was very different for all these folks, the project assumes the latent variables aren't normal. Actually assumes them to be categorical and discrete, so that each person, if you think of it as an ability that you might learn in the class, it's an ability that something you're learning, like a skill, you've either mastered it or not, rather than trying to find a continuum of mastery. High masters are 2 points higher than low masters and so forth. So this discussion just happened with a bunch of fairly well-known professors that I had prior to this, and so it sort of emboldens me to teach you this today, because none of them had any clue, mostly. One of them who wasn't a professor who works at ETS is great. Most of them are like, well, it's not a continuous thing. How do we do that? And so it's just something to think about as you go forward. We'll quickly leave it. We'll be stuck in normal distribution land, but just leave space in your mind to unlearn that when you go forward, okay? Questions? Do any of you have questions on the first thing that we started? Any of you like Coke Zero? No? Yeah? Maybe? I like real Coke. That's like crack cocaine to me. But I can't drink it all the time. But Coke Zero tastes the closest to it. So. Anyway. I lived near Atlanta for a number of years, and you get to know that's Coke. Everything's a Coke. If you did a Pepsi, it's a Coke, right? A Sprite's a Coke. Mr. Pibb? No. It should be, yeah, but no. Yeah. Go figure. All right, so what we talked about before was marginal distributions. One thing, one variable, one two-dimensional graph, although we sort of have a multivariate normal on the first slide. We want to now talk a little bit about joint distributions. These are data that you observe all at once. Right? I said height and weight. That was one thing. Another part of this is if you give out a survey, like the 5-item happiness scale, the 5 responses to that survey have a multivariate or joint distribution that we need to describe. Each of those is a variable by itself, but together you're modeling all of them all at once. So you have to think about what the joint distribution happens to be. And it's especially important because in SEM, if we don't think about the joint distribution and we don't fit the joint distribution well, our model does not quite match the data, then anything that we start to say about our model, of course, is not valid, maybe biased. So it has a real big implication in SEM. If you've looked at studies in your field where confirmatory factor analysis comes up, or SEM, I don't know if you've any of you seen those, they start to talk about model fit a great deal, and they say they have letters that just start showing up like CFI and TLI, RMSEA. Some of you who did Levon in R last week for homework 1, if you've done it already, you may have seen these numbers. All of those are indices of how well your model fits a very specific joint distribution, the multivariate normal distribution. So all of that is something we have to consider when we're going forward. So there are several types of distributions. When we have one variable all by itself, it's a marginal distribution. When we have 2 variables at once, it's a joint distribution. There actually are distributions that are called conditional distributions. That's what happens in regression. Right? You can think, oh, regression, is that 1 variable or 2? Right? Because you've got y and you've got an x. Let's say a simple linear regression. You've got y, it's predicted by x. Is that 1 or 2? Well, really what you're looking at is a univariate conditional distribution. So given x, here's what y's distribution should be. Right? And actually the predicted value is the mean of that thing. And that predicted value follows a line. So the mean of y follows a line itself. But if you were to kind of take a snapshot of each part of the regression line, it would be the mean, and you can draw a normal distribution around it. So that also shows up. A lot of the funny debates we get into in, if you ever submit a paper, if you're not a methodologist, they submit it to a more of an empirical journal. Some people call it substantive journals. I like to think what I do has substance too, so I call quantitative methodology is a substantive area. But if you submit it to your empirical area and people will argue about certain things about your statistics, a lot of times it's arguing about the type of distribution you have, even though those aren't the words. Is it a marginal or is it a conditional? Because you do things a little bit differently if you know the knowledge of each. So, anyway. So, marginal distributions we've worked with all the way up to here. We had the 3 continuous univariate distributions, uniform, normal, and chi-square. We didn't get into categorical distributions, mainly because I want to wait till later in class. I'm already going to overwhelm you enough. So I do have limits. It may not feel like that, but speaking of, quick question, sidebar. Was the reading appropriate length last time? Like 1 chapter, 1.5, 2? Yeah? No? Maybe? Okay, good. Just hoping it's doable. The optional readings, you pick those up, 60 pages, I hear? Reference. Or if you're a REM student, pre-comps. Oh no, I just made more worry. Never mind. No. And besides, I'm on your side on comps, folks. My strategy is this: they shouldn't be the way they are, and you know this. Maybe the ones of you who have seen me in class before, I've adamantly argued for this. We'll see how they come about for those of you who are going for it. Anyway, back to the distribution. The discussion about distributions. There are names of categorical distributions: Bernoulli, binomial, multinomial, and Poisson. We try not to get into those, but really what we're after is the joint distribution itself of a variable. And again, I said this on the slide that had the picture of the multivariate normal. It works the same as the univariate. Remember before we're like, what's the height? What's the height? What's the height? You plug in data, you get a height. Right? Same thing works for the multivariate or joint distribution. It's just instead of plugging in one piece of data, you have to plug in multiple. Right? You had that multivariate normal and you collected height and weight. Now you plug both height and weight in, and it tells you the overall one height from it. There's only one height of the distribution. It's just you're plugging in multiple things. And that's where you start to see these graphs that start looking weird, 3 dimensions and so forth. I can't graph a 10-dimensional space. It's not going to happen, but that's what we end up getting into. So, the term multivariate distribution and joint distribution the terms are synonymous, right? So a joint distribution is the same as a multivariate distribution, right? Multiple variables go in. You collected multiple things. You plug those multiple things in to get the height. But unfortunately, discussing multivariate distributions means we have to sort of talk about matrix algebra, because most of the language of multivariate distributions shows up in matrices. But bear with me. I'm going to try to make this a streamlined approach to matrix algebra. Any of you have taken matrix algebra or linear algebra before in class? A few of you have. But I took that the end of undergrad. That was kind of blew my mind. It was fun. For those of you who haven't, and for those of you who have, actually, you'll be able to point out my flaws to this, but I'm trying to come up with a didactic way of giving a very brief primer on matrix algebra. Here we go. So, starting over. Let's start with definitions. Again, what is a matrix? A matrix is a rectangular array of numeric or algebraic quantities subject to mathematical operations. It's a box of data. It's also a substrate on or within which a fungus grows. I didn't know that. Use that at your next trivia, right? The matrix is where fungus grows. I'll try to keep this fungus free. Algebra. And so, Devane, I was asking you, you had said algebra was high school? This is a lesson in algebra today. Algebra, I had to look this up because what is algebra? Do you remember your algebra class? I remember in junior high I had like the pre-algebra, or what, I don't even know if that was it. I don't think it was pre. No, I had anyway some algebra-based thing, and I remember they put y equals x plus 1 on the board, the very first, and I was like, what is that? Z, or V T U V X. I failed breathalyzers all the time. Anyway, the algebra is basically a branch of math where we put symbols in place of numbers, so it's meant to be general, and then we do things to the symbols. We do operations to them, right? So we may add symbols. We have to come up with something called an identity, right? What is a symbol itself? What's essentially the number 1 is the identity. We have operations such as commutative or associative or distributive, right? There's certain ways that we're able to distribute numbers that aren't actually numbers, the concept, the placeholder of number itself. So matrix algebra puts the two together. We have a box of data. We represent that with a big capital letter that's in boldface, and we do algebraic manipulation to it. But really, what it works for in general, though, is to shorten the notation. Matrix algebra should be your friend. Right? It makes things that are really, really long and tedious to write notation-wise very compact. The end of my lecture last week, I had the path diagram with all the 5 observed variables, the 1 latent and the 1 predictor of the latent, and then below that I had 6 regression equations. I probably could have expressed that in like 3 matrices to make it work fast, right? So instead of having all that long list of whatever, it's this. So that's what you see if you get into some of the optional readings that we're going to get into involve David Kaplan's book. David Kaplan's book is like this thick, right? It's this thick because it shortens all the notation into matrices. And so having my background being cognitive or psychology with a little bit of cognition thrown in, it's the idea that you need to understand what that placeholder represents. It's kind of a language. And so that's where we're getting into today. So I don't want you to do anything with matrices other than just appreciate that they exist and we use them to describe distributions. If you can get that far, that's cool. Another benefit, hopefully, is that if you get into something, if you're learning about a new method in statistics that might have just come out and you want to use, or perhaps your advisor wants you to use, your colleague does, you go to the primary source, you might see matrix algebra. You can hopefully come back to some of the materials that you had from this class, maybe the slides, but also the readings, and sort of try to disentangle what each of the equations and formulae mean. for it. But that's the high end of what I'm looking for here. So just sit back and listen. There's no quizzes on matrices. There won't be, and we won't be doing matrices. They will but they will show up, and I want you to have that conceptualization. Check that. There's one place where in R you'll have a matrix, but R matrices and R what you're doing in Lavon are not going to be any different. In fact, we're going to use matrices in Lavon. There. All right. So not outside of Lavon, not outside of that. Oh, data in R. Speaking of, okay, so I have an example data set. I created, imagine I collected SAT scores for 1,000 students. They had SAT math and SAT verbal. You know, come to think of it, I think I made this example when I taught my first class here at Kansas, like 2000 and, whoa, long time ago. The way back when all of you weren't even born yet, in high school or whatever else. Anyway, so yeah, sorry, just hit me, yes. I should probably change my example. I have actually modified it. The data there are the same. Anyway, we have these data. You could think about it this way. We have SAT math, SAT verbal. Any one of those variables by itself is a marginal distribution, but we're going to build towards working on the joint distribution. And so typically when we look at variables, the descriptive statistics show up. Like we have descriptives up here for SAT verbal, the mean and standard deviation. Same thing with math, mean and standard deviation. Those are descriptives on a marginal level, right? But if we were to describe both variables together, we start getting into something like a correlation matrix. And that's a joint descriptive, right? You have to have two variables to talk about a correlation. 0.78 is the correlation between SAT math and SAT verbal. So let's go into some definitions. Matrices, vectors, and scalars. Boy, I remember when I was failing math, I used to hear people talk about these things and think, yeah, nerd, right? Oh, how I've become one. Anyway, I prefer the term all-star. This is a matrix. A matrix is a rectangular array of data. All it is just a box of numbers. Think of it that way, right? So rectangular is an odd term because we typically think of a rectangle having two dimensions, like rows and columns or length and width. But technically speaking, it can have volume. We could have 3, we could have 4. We could have all sorts of weird data. But for us today, we're having two dimensions. We'll have a row and a column. That's it. So we'll have a two-dimensional array of data. And here's an example. This box down here is a matrix. This has all 1,000 people from my sample in it. Right? This first thing is SAT verbal. It's column 1. SAT math is column 2. Right? And so the size, we describe the size of this matrix as being the number of rows by the number of columns. So there are 1,000 rows. Each person takes up a row. Each column, there are 2 columns. Each variable takes up a column. Okay. The size of matrices is important because the algebraic operations sometimes don't work unless the sizes correspond. A matrix multiplication is the problem. We'll get to that in just a bit. So, how do we denote matrices? Typically, when you're reading a stats paper or journal, a matrix is in boldface and in capital letters. Right? It's like screaming, X. That is the matrix X versus something else. When I draw matrices, if I would draw them on the board, I can't really bold well, but sometimes I put a little half arrow on the top of it. Does it say? That would be it. So, a vector is a matrix where one of the dimensions is equal to 1. Right? So this is the top value there is called a column vector. Right? That looks like it is SAT verbal. So you can think of a column vector being just one of our variables. Yeah, that's 1,000 people, observations on one variable, 1,000 by 1. Alternatively, a row vector is one of the rows. Right? This is the first person's data. This is their SAT verbal and SAT math. It's size 1 by 2. There's 1 row and 2 columns to it. So a couple other notes on notation. A lot of times you'll see whereas a matrix is in a capital letter, like X, capital X before, a vector is in a lowercase letter but also bold. And if it refers to a part of a matrix, so when you go back a slide, the big matrix X really there's two row vectors here, right? There's x, sorry, two column vectors. There's x, all the rows 1. I put a dot to represent the dimension that has all the people in it. So x dot 1 represents the first column and all the rows. And then this other one would be x dot 2 similarly. Okay. So again, they're in boldface because these are matrices. They're just special matrices, vectors. And the dots represent the aggregation. We just talked about that. The numbers within a matrix are called the elements of the matrix. Right? So this first value right here is person 1's first variable, right? Or element ij. It's the row position by the column position. All right, so this is row 1, column 1. This other value right here is row 1, column 2, x1, 2. And eventually, when you start getting into double digits, you might see commas separating the two dimensions. So the last person 1,000th, first variable is x 1,000, comma 1, and so forth. These are the numbers that you know so well. Those are just what you knew before, numbers by themselves. They also go by another name. The word is scalar. A scalar is a single number. Why? What does the term scalar conjure up in your head? Let me think here. It makes me think of the word scale. Makes me think of limestone or calcium deposits. No, I don't know. Wait a minute. In this class, a scale is an instrument, right? Scalar, the idea of a scalar, the reason why it's called a scalar is because it has a special way it works in matrix algebra. A vector can actually be used to indicate the length of something or distance between points. And if you can talk about length or distance, if you multiply that vector by a single number, it will change that distance. It will rescale it. Right? So you may want a distance. A lot of times, actually in statistics, if you do exploratory factor analysis and you're using the older techniques that involve matrix algebra, actually. First of all, don't tell me you did it, I don't like it. But second, we have to, one of the ways that it works is that each of the outcomes have to be a vector of length 1. It's almost like a factor almost. The way that it becomes a vector of length 1 is we figure out the length of this thing and we divide by it. Rescales it so it's length 1. So that's it. That's all it is. A matrix consists of a box of scalars. How we doing? Awesome. I love that the weather is even good for this too. It's like a day that you want to be outside, and here I am talking about scalars and vectors. Really? Yeah. So the first thing we want to talk about with a matrix is one of the operations on it. This is like algebra. It's called the matrix transpose. Right? A transpose, all that it does is for every element in the matrix, it transposes the row position with the column position. So before, what we had was this 1,000 by 2 matrix. If we transpose the row and the column position for every person, we actually flip the dimensions. It's a 2 row by 1,000 column matrix that we end up with. Each element in the matrix transpose literally takes its column position and swaps it with its row. So for instance, 580, what is its position? What's the row position of 580? This is x1, 2, right? Column 2, right? Down here, it happens to show up as x transpose, row 2, column 1. So literally, it just swaps each of the positions. Right? Xij becomes xji. That's it. We've just resorted our data. We notate it with a capital T. There's other ways that people sometimes do that. Sometimes people use the value x with a prime symbol by it. I like the letter T because prime sometimes involves in other math terms like derivatives and so forth. But x transpose. And why we use transposes is because matrix multiplication generally. What we end up doing from matrices is we look at a bunch of our non-matrix terms, like when we have these series of equations, regressions, and we see the terms that we might be able to lump into a matrix. Often there's something that has to multiply something else. What we want to come up with is the matrix version that gives us all the single equations. And sometimes we have to pick one of these matrices to be the transpose, and sometimes the other one is. It's kind of arbitrary, but it works, so that if you were to do the longhand math to figure out what the product of two matrices would give you, it would be all the equations back again. So transpose is our wiggle room with trying to build a matrix. Sometimes it needs to be there. So there are certain types of matrices in existence. There is a square matrix. Square matrix, as you might guess, looks like a square, whereby the number of rows is equal to the number of columns. Correlation matrices are square. We talked about covariance a little bit last week. We're going to talk about covariance a lot next week. It's square. Right? You can think of lots of different square matrices. A diagonal matrix is a matrix that has numbers down the diagonal and zeros in the off diagonal. I feel like this is kind of like a word search game that I'm playing up here, number search. But yeah, it's a diagonal matrix. Those are the values itself. Diagonal matrices don't really show up in your books very often, but they do come in handy. If you had a covariance matrix, how many of you have heard of covariance before? Maybe a little bit, right? Covariance matrices have the variances down the diagonal for each variable and the covariance the off diagonal. But you can go from covariance to correlation if you divide each covariance by the square root of this variance of the first variable times the variance of the second. And you can achieve that through multiplying three matrices together, two of which are square matrices with just that diagonal term in it, the variances themselves. So, finally, a last term that we're going to talk about in terms of matrices is a symmetric matrix. A symmetric matrix is a matrix where all the elements on the lower part, the lower triangle, are reflected about the diagonal for the upper triangle. So essentially this element here is equal to that element, this element is equal to that element, and so forth. So a correlation matrix is a symmetric matrix. A covariance matrix is a symmetric matrix. A distance matrix is a symmetric matrix. Right. So we're familiar with all these things, right? All we're doing is adding labels to some of the things you've heard, and we talked about vectors. Scalar you knew before, matrices, okay, probably, but vectors are a little weird. So let's do a little bit more on vectors, shall we? This is where the thing gets really trippy for me. Vectors can be used to describe physical dimensions in space, or coordinates. So here's a coordinate system, and we could take the vectors A and B such that the first element might be its value of the x-axis down here, and the second element might be the value of the y-axis. Right, so this is 0.12 right there, and this is 0.23. That's a nice graph. All right. A natural part that comes from that then is, what is the length of this vector? And what is the length of that vector? You remember geometry? Oh God, here we go again, right? Oh, this is a right triangle. That is the hypotenuse. You can find the length using the square root of the hypotenuse. Holy cow. But we're not there yet. Here's the first thought. That sounds great. These are nice little two-dimensional vectors. What happens if we were to plot how would we take our column vector of SAT verbal or SAT math? How would that look for a plot? It would be out in 1,000-dimensional space, right? There's two little dimensions here, right? X and Y. We have 1,000 people, right? So that vector is pointing off. I don't know where 1,000. It's just like up there. It's like the 7th floor to me, right? It's up there. I don't go up there. Does anyone of you work on the 7th floor? Oh, you all work up there. It's where the vectors end. Anyway, yeah, I'm slumming it on the 6th floor. But yeah, I'm really happy with my office. I love it. But anyway, point being, it's kind of an interesting thing. I can't think about what 1,000 would be, but I can think about what 2 is. And if you can think about what 2 is, then if you understand what length for 2 is, length for 1,000 works the same way. It's kind of a weird deal. So vectors can get added together, right? So we have here, what if we wanted to add the first and second vectors together? We just add them element by element. Although there is one catch, the vectors have to be the same size. All right, are these row or column vectors? Column vectors, right? That means they have two, actually there's 2 rows and 1 column. The 1 in the column is the indicator for the column vector right here. So this first vector size is 2 by 1. The second vector size is 2 by 1. So if they're both the same size, we add them together element by element. 1 plus 2 equals 3. 2 plus 3 equals 5. So really, if you think about what we just did, with this one equation right here, C equals A plus B, we've just computed actually 2 different sums simultaneously. And that's the kind of the purpose of matrices. It makes the math go quicker. We can do the same thing with our data, right? SAT total is a sum of column vectors. They're both the same size, 1,000 observations by 1. So we end up with SAT total, which is a column vector that's 1,000 observations by 1. And here's what happens geometrically. Here's vector B down here. I like the KU colors for the most part, although the purple up there just really distresses me. Is there any truth, those of you who are from the state or been in the state a long time, any truth to the rumor that if you add blue and red together, you get purple, and that's where K-State got their color? I just wanted to know. I like purple, personally. I like blue and red better, as you can see. But anyway, there's A, there's B. If we were to add both of them together, it would be like taking B and putting it at the end of A in the same angular way. Like if this was, the origin was down here, if you just took the origin for B and put it up right up here, right, the length of the new vector would end up where the end of B happens to be. Right? It just adds one on top of the other. So it has this weird geometry to it. Okay, moving forward. What we can do also with vectors, and this is where scalars get their name, is we can multiply them by a scalar. Right? So if we had vector A here, and we multiply it by a scalar that's valued 2, anything that is multiplied by a scalar, each of the elements in the vector or matrix is multiplied by that number. Right? So you get a value of 1 times 2 equals 2, 2 times 2 equals 4. And although I just described to you, oh, here comes length again. I talked about length. Right? This is a right triangle. If you look on the axis here, the length of this one is 2. The length of that is 1. So this hypotenuse length has to be 2 squared plus 1 squared, or the square root of it. Right? The Pythagorean theorem. I've heard of this thing before. Don't drink alcohol before class. I mean, actually, it might help you. It does not help me if I do. Anyway, it's the Pythagorean theorem says that the hypotenuse, the square version of the hypotenuse, has to equal the sum of the squared lengths of the legs of a right triangle. So this thing's length is 2 squared plus 1 squared, which is the square root of 5, right? If we were to do that, look at what happens to it when we multiply it by a scalar here. What happens is it changes the length ever so slightly. Instead of having 2 squared plus 1 squared, we now get 2 squared plus 4 squared. So the length was no longer the square root of 5, it's now the square root of 20. Right? So it's just made it longer. And so if you have scalar multiplication, this is me trying to steal graphics. What you have here, if you have a vector v and a vector u, and you multiply them by a positive scalar, they get longer. All right, that's what happens. If you multiply them by a negative scalar, they go in the opposite direction and get longer. And then finally, if either of those scalars are an absolute value less than 1, they actually get shorter. They shrink. They're fractional size. So in the general linear model, believe it or not, the fixed effects, the slopes, the beta weights, those are scalars. And there is a pretty cool geometric version of regression in ANOVA, the linear model, where you've got weird angles of vectors and matrices projecting onto each other. It's cool in some respects if you love geometry and vectors and whatnot. It's kind of like statistics trivia otherwise. I took a class on it once, and it was like learning statistics in French, like a different language, right? It was all like, okay, this is a flower and the flu, like you've got names for other things, but the same quantities. Anyway, how are you doing? Questions? Making this hopefully a little bit seamless. Linear combinations show up in data often, right? So a linear combination is a set of vectors multiplied by a set of scalars, all added together. Right? Like regression, right? Regression is a linear combination, essentially. Although I didn't put regression into matrix form, but we could. And actually, next week we will. So, linear combinations happen really frequently. A regression in ANOVA, principal components analysis, structural equation modeling, all of the above happens there. The reason why we talk about it is there's a certain linear combination that results to something that's bad for us in statistics, and that's something called a linear dependency. Right? If you have a set of vectors where you have it possible to create a linear combination that equals 0 when all the scalars are not equal to 0, you have something said to be linearly dependent. So for instance, remember how we took SAT total? Okay. We added SAT verbal plus SAT math, and they were both times a scalar of 1. Let's take a look at the 3 variables we had now. SAT verbal, SAT math, SAT total. There is a way that we could come up with a series of scalars, 1, 1, and -1, such that the sum of these three things equals 0, meaning these are linearly dependent. Have you ever done an analysis where you've put 2 variables and their sum in? So for instance, I can imagine, if we're in the SAT world, we'd like to know how our freshmen are doing in college here that we've admitted, and let's imagine they don't take the ACT, although I hear ACT is like a Midwestern thing. They took the SAT, these students. Maybe you're over there looking at results and you're saying, hey, how does SAT relate to first-year GPA? Right? So you put in SAT verbal and you put in SAT math and you do a regression, and maybe your supervisor says, hey, wait a minute, why don't you put the total in too? Right? Have you ever done that before? You know what happens? It breaks. What's it? Singular matrix, that's right. You end up getting multicollinearity that blows up, right? Ever heard of that? Multi or just collinearity? It's a linear dependency. It literally means you've got some variables that can be described by a series of others. I think a lot of people make a big deal about collinearity when they've got nothing else to criticize for your data. The way I look at collinearity, how you know there's collinearity, is either the computer doesn't give you a result or it gives you a warning, or the standard errors for each of your variables are an order of 100,000 times bigger than the estimate for each of if you have a beta weight of 4 and the standard error is 400,000, that tells you there's something wrong, right? So, okay, so that's literally where collinearity happens. So that makes you think, collinearity, actually, the technical term of this is that if we were to put all 3 of these in a matrix, we can't invert the matrix, but that's something we'll talk about in just a few slides. Right? It's like dividing by 0, essentially. Doesn't work. Okay, so one thing we can also do is compute something called the dot product, or the inner product between 2 vectors. This looks like vector multiplication, right? A dot B, but it's a little bit more complicated than that, right? It literally, if it was A dot B, what you'd think about, let me go back to a slide with A and B, like right here. To me, A dot B would be the number from the first one multiplying the number from the second one, right? Not so easy, right? That's involved in it. It's the number from the first times the number from the second in the same element position. But then that's now added to that same sum of the product from the next position. So A dot B here would be 2 or 1 times 2 plus 2 times 3. So this would be 2 plus 6 or 8. So it's an odd way of looking at it, and there's a reason for that. Of course, there's always a reason. But what ends up happening is when you look at it that way, what you can do, and we sometimes express this as a matrix A in a matrix multiplication sense, multiplying B, but I haven't described multiplication yet. But essentially, that's just it. It's a dot product between rows of matrices, rows and columns of matrices. It gives us the product of two scalars in an order in each of the vectors. And then when that sum happens, well, we use this to our advantage in statistics because we happen to have a lot of things that has summation terms. Right? For one, we could talk about variance or covariance. So we end up getting certain matrix products or certain dot products in equations because a lot of times they take the place of things that would be a sum. That would be an uglier thing to write, the sum of a lot of things altogether. We could just express it with this matrix transpose times that matrix, and it's a result. So what does this really matter? If we were to do this with our SAT data, our number was very big, 251,928,400. That represents something that's related to the angle between the vectors. What do I mean by angle? Well, these are 1,000-dimensional things, but going back to this first slide, if you look at this vector here, this is vector B, and vector A, their angle from the x-axis, right, is this right here. Right, that's how many degrees is that vector off of the x-axis. There's that degree for the B, and there's this other degree for A. The distance between these two angles is this dot, is related to the dot product. Just normalize this, really. But what happens, why is this important to us? Think of it this way. These are data. What happens if our data points are perfectly on top of each other, if the angle distance is 0? It's actually like saying we have a perfect correlation in our data. Okay. So angular distance between vectors is related to correlation in data. It's this angle of a 1,000-dimensional vector object that goes up to the 7th floor, up there with Alan and Jennifer, that ends up being the thing that differentiates it for us. So. Anyway, I'm trying to make this a little bit more real and understandable. I'm going to stop there with that part. We still have about 5 minutes. I'm going to get into matrices. The reason why I described vectors first was because matrices are boxes of vectors. So we just want to put those together. And a lot of the same vector operations exist in matrices. In fact, every one that we've seen, vector addition, vector multiplication by scalar, and the vector dot product, all correspond to things in matrices. So this is where I'm going to bring in the idea of algebra, or what I remember of algebra. Right? Algebra is a bunch of symbols and then the operations on them, or so forth. So the operations I want to talk about are pretty basic. Addition, subtraction, multiplication, division. If you have a box of data and another box of data, can we add the data together? Can we subtract it? Can we multiply it? Can we divide it? The answer is yes. We just have to show this form. Also in algebra, we had to talk about an identity matrix. Identity, the number 1 is the identity. The thing that multiplied by a variable gives you the variable back itself, right? The value of 0, the nullifying, right? Anything times 0 is 0. We have that same value in matrices as well. And then finally, we actually have a unit vector, or one, actually it's not a unit vector, it's a vector of just ones. And this actually helps in a lot of our statistics. So you'll see ones show up in places before. Mainly because when we do a dot product, remember one of the variables keeps getting multiplied by the other element. If one of those variables is just the number 1, anything that dot products it becomes the sum of itself. Right? When have you seen the sum of x before? Like second day of statistics, right? Anyway, it's a shortening thing. Okay, starting with matrix addition, subtraction, you'll like this one. Works the same way as vector addition and subtraction. Matrices have to be the same size, same number of rows, same number of columns, and when that happens, right, just add each element together, or you subtract each element from each other. This is a quick little demonstration. Here's a matrix A. What's its size? How many rows? 4. How many columns? 4, 2. 4 by 2. Is B the same size? A, we could add A and B. A and B is just each element of A added to each element of B. Or we could subtract A and B. Ironically, subtraction is really addition, but when we multiply B by the scalar -1. Right? So if we multiply all of B by -1 and then add it to A, we end up getting each element-wise subtraction. Matrix multiplication is the one that's crazy. For matrix multiplication to work, we have to have two things that matter. You have to have the order of the matrices. Has to be precise. You have a matrix that shows up first. It's called the pre-multiplier. So this is like A right here. This is a pre-multiple. And B is a post-multiplier. And the reason for that is, to make matrix multiplication work, the number of columns of the pre-multiplier has to be equal to the number of rows of the post-multiplier. It's kind of an odd thing, but we'll see why in just a moment. It involves the dot product again. The new resulting matrix has the number of rows equal to the rows in the pre-multiplier, and the number of columns representing the columns, bless you, in the post-multiplier. So, I saw this when I first started taking matrix algebra, and I was like, oh, come on. That's just too much. Why can't you just... No, but really what it happens to be is that each of the elements of C come from the dot product. Remember the element, that's the specific cell. That is the dot product of a row vector in A and a column vector in B. Right, so if you think of that row vector and that column vector, right? Remember the dot product is element by element, multiply each other, add it up, multiply each other, add it up. That dot product represents that element of C. So, for instance, this is the matrix C here. The term highlighted in red is in row position 1, column position 2. So it is the dot product of row 1 of A times row or column 2 of B. Remember the dot product, it's first element times the first element plus second element times the second element, and that's what this happens to be right. Same thing, if you wanted to know where this comes from, it's figure out the row, it's row 3, column 4. Takes row 3, that vector, and multiplies it, dot product, row 3, column 3. Pardon me. 3. Helps if I get it right. Row 3, column 3. This is in row 1, 2, 3, column 3. This one, that one. How we doing? Is that weird? Why? Well, here's a matrix form that shows up quite often. X transpose X. It's crazy, right? Matrix transpose times itself. Well, what size was X? It was 1,000 by 2. So its transpose was 2 by 1,000. So 2 by 1,000 matrix times a 1,000 by 2 matrix. The rows of the pre-multiplier match the columns of the post-multiplier. So we could do that. And when we do this, look what happens. Down the diagonal, we get the sum of the squared variable. Sum of SAT verbal squared for each person. Sum of SAT math squared for each person. Remember where we've seen sum of squared before? Variables? Variance, right? Variances. This shows up a lot in variance. In the off diagonal, we get the sum of the product between variables, sometimes called the cross product. That thing shows up in covariances. This matrix is an analog to a variance and covariance matrix. And rather than having to write it out where I have each one of these terms with the sum by it, I can express it for all of my data for any type of number of variables with just this right here, x transpose x. So anything that you see in statistics, I know we're up against a break, that involves some type of scaling or some type of variances, x transpose x is usually lurking. Right? And really what it does is serves to take the place of all these terms. So I'm going to stop there. Let's take a 10-minute break and come back at around 3:30, okay?